Hey everybody. So we were talking about lines in the last video, and we're going to continue to talk about lines. I just want to do some examples. I think last time we defined what a line was, so let me remind you of that. When we talk about lines, we'll have what we call the vector equation of a line, where r is going to be the vector. So what this vector is going to be doing is pointing at points on our line, right? So we find a vector that points at one known point, and we have a parameter t, which is used as a scalar for the vector v, which is in the direction of the line. So the picture is something like this. Let's call this the origin. I'm not going to draw all the axes. They'll make this drawing more confusing. So we have a vector r naught, right? And that's pointing at some point on our line. And then there's going to be a vector v, right? So I'll draw this as v. And then when we scale v, right, I've drawn it as scaling larger, but it can be either way. It can scale in the negative direction. We get tv, and that's what we add to r naught to get r, right? And so let me pencil in or pen in that represents the line. And so as we scale v, we point at different points on this line. Okay, so that's our setup. Let's do an example of finding a line given 2 points. So right, we can think it's in some ways very similar to in two-dimensional case, though we don't formulate it exactly the same way there. But in general, right, if you have a point and a line, point and a slope, which is like having a point and a direction, you know the line. Sometimes you're given 2 points where we can use those 2 points to compute the slope, which gives us the direction. We'll do a very similar thing here in 3 dimensions. So suppose we want the equation of the line through, and our 2 points will be 7, 3, -1, and 4, 1, 3. Okay, so just to imagine it, again, I'm not going to try to draw a terribly accurate picture, but we've got 2 points and we want a vector equation for the line through this. So remember what we need. We need a vector pointing at a point on the line. Well, we've got 2 to choose from, so that's going to be pretty straightforward. We can choose either one. And then we're going to need a vector that points in the direction of the line. Well, there's an obvious choice that we can make, right? The vector between them, right? That's going to be in the direction of the line. So that will be v. So in this case, I'll take, remember, if we want to find the vector between 2 lines, we can take the coordinates of one, subtract the coordinates of the other, right? Either direction. It doesn't matter in this case. It'll change which way v faces, but we're happy with either one. So we'll get 4 minus 7 gives me -3. 1 minus 3 gives me -2. 3 minus -1 gives me 4. And there's my vector v, right? And then for r naught, I'm just going to choose this point, right? So what we're saying here, so my vector goes from this point, v goes from this point to that point, and I've chosen r naught to point at this vector v, right? So I'm imagining the origin over there, and I've got r naught pointing at this one, and then when I add scaled versions of v to it, I get all of these. And so it's simple enough to now just write our vector equation. We get r equals, just following this, r naught, 7, 3, -1, plus t times v, which is -3, -2, 4. Okay, and if we want to write it a little differently, I can multiply the scalar in here, and then I can add these 2 vectors together, and I get 7 minus 3t, 3 minus 2t, -1 plus 4t, right? So there's a component form for this vector equation. Notice something, because of the choices that I made, if I take t to be equal to 0, then r is equal to, right, all these t parts of this equation disappear, and I get 7, 3, -1, which is what we called r0. And at t equals 1, r is equal to, well, just putting in 1 for t, 7 minus 3 is 4, 3 minus 2 is 1, -1 plus 4 is 3. And that's the other point, right? This is the position vector pointing at this point, right? R0 was the position vector pointing at that one. And so because of how we set it up, right, we get this idea that it starts at this one, and at 1 it starts pointing at this point, and at 1 it points at this one, right? We could have made different choices and it could go in the other direction. But this gives us an idea for something that we often want to do, which is suppose, so we're going to do a similar idea to this, just a little more abstractly. Suppose I have 2 points in space, and I want to make it so that, let's call, here's a point, here's my origin. I'm gonna draw a vector from the origin to this point and call it R0, and a vector from the origin to this point and call it R1. Suppose I want to come up with the vector equation not for the line, but the line segment, just the piece of the line between these two, okay? Well, we can do a similar thing that we did up here, right? What did we do? We found the vector between them. I'll use red here. So the vector between them, which is v, can be found just by taking R1 minus R0, right? We start with, when we have our vectors aligned this way, if I take where I finish, subtract where I start from, I get the vector between them, right? And then the line segment between them is given by our standard equation, R0 plus TV, but V, remember we said, is this, right? And notice what happens, just like what happened here, if t is 0, this disappears and r is just equal to this point, and at t equals 1, we get R0 plus v, we end up with the vector R1. So at 0, this equation, the vector is R0, and at 1, r is equal to R1. And so if we limit t between 0 and 1, then this vector equation only spits out the line segment, okay? And there's also a neat configuration of this thing. If I expand what's happening on the right there, I get t times R1 minus t times R0, which I can rewrite as, so I'm combining these two terms, and I'll get, well, let's just write it, R0 minus t R0 plus t R1, or 1 minus t R0 plus t times R1. And I think this one gives a kind of neat understanding of what's happening here. When t starts out at 0, this is a 1, this is a 0, so all we get is R0. As t increases, we're subtracting more and more from 1, so we're getting a smaller coefficient to R0 and a larger coefficient to R1. In other words, as t goes from 0 to 1, we get less and less of R0 and more of R1 until we get to 1, this piece disappears and all we're left with is R1, right? So geometrically, when we're somewhere in the middle, we're getting some portion of R0. Maybe I'm only look to it in red. Maybe when, let's say when t is something like 1/3, we would have 2/3 of R0, so we might go out this far. and then we'd have 1/3 of this, which might be something like that, and put us 1/3 of the way along this line. We're getting mostly R0 and a little bit of R1, and as t increases, we get less R0, maybe just to there, and then we get a whole bunch of R1, and then we're out there until at the end, we're getting entirely R1, okay? Okay, let's do another example, okay? So let's talk about the notion a little bit of, we've probably always felt like we understand very well what are intersecting lines, right? If I have two lines and they share a point, they're intersecting. When you first learn about lines in geometry, you probably hear something like parallel lines or lines that don't intersect, but we've had to change that, that understanding now because we're in 3 dimensions, right? So we said earlier in these videos that parallel lines now mean lines whose vectors are the same direction, right? Sorry, whose vector v, their direction vectors, are in the same direction. And we say that vectors are parallel. Sorry, I'm saying that unclearly. 2 lines are parallel if their direction vectors are parallel, and 2 vector directions are parallel. Vectors are parallel if they're scalar multiples of each other, right? So here's think of my pens as vectors. Here they are both, here they are parallel. They're in the same direction, right? One's facing the other way. They're still parallel. You can imagine scaling one, making this a little longer. It would still be. Here's the thing we don't have in 2 dimensions. I can have 2 lines, right? So this one's now above that one. They're not in the same direction, right? But they also don't intersect. And so we can't just talk about whether or not lines intersect to understand if they're parallel. Parallel, we want to capture that idea of the same direction. So what we call these kind of lines, when they are not parallel, meaning their vectors aren't in the same direction, but they also don't intersect, we call them skew lines, okay? So we can take any 2 pairs of lines and say they are intersecting, parallel, or skew, right? Parallel is the easiest to identify because they, their direction vectors, the v, right? Or if they're given in symmetric equations, right, you can look at those direction numbers. They're gonna be multiples of each other. If that's not the case, they have to be one of these 2. So let's take a look at a couple of lines and see if we can determine if they fall into one of these categories. So let's look at the line R1 is equal to 2 plus t, 3 minus t, and 2t. And the line R2, which is going to be 1 minus s, 1 plus s, 3 plus 3s, right? So if you look at the direction vector here, the v, it's going to be the vector 1, -1, 2. And the direction vector here is going to be -1, 1, 3, right? I'm getting that by just looking at the coefficients of t, because those come from, right, t times the vector v, so the coefficients of t, when we write it this way, are where we got, it came from v, from the direction vector. So now it's clear they're not parallel because, right, if I multiply v1 by a number to make it equal v2, well, to make it match in the first component, I have to multiply -1. That will work for the second component, but it doesn't work for the third. So they're not scalar multiples of each other, right? If I make it so that the third match, neither of the other 2 will. So there's no way to make a scalar multiple, make one of these a scalar multiple of the other. So they must either be intersecting or skew. So what does that mean? If they're intersecting, right? So let's write an equation, let's write the parametric equations for the 2 lines. I'll call them L1 and L2. And I'm just rewriting this. L1 has x coordinate 2 plus t, y coordinate 3 minus t, z coordinate 2t. L2 has coordinate, x coordinate 1 minus s, y coordinate 1 plus s, and z coordinate 3 plus 3s, okay? So if they intersect, what does that mean? It means that there must be a value of t and a not necessarily the same value of s. It could be different, it could be the same value, we don't know. Most likely it's not the same value. But one single value of t and one single value of s that when I plug them in, they spit out the same 3 coordinates, right? That would be a point that they share, okay? So we have to figure out how to find those two. So let me write this out a little bit with some symbols. In other words, what I'm saying is, let's call these x1, y1, z1, and these x2, y2, z2. We need to find t and s, a single value of t and a single value of s, so that x1 of, let's call it t star, equals x2 of s star. And y1 of t star is going to equal y2 of s star. And z1 of t star is going to equal z2 of s star, right? This is a system of equations, right? There are 3 equations, and we've got a couple of unknowns. So let's try to solve this system. I'm just going to look at the first 2 equations. I'm going to start there. This is the equation 2 plus t equals 1 minus s. And the second equation is 3 minus t equals 1 plus s, right? So again, let me state what I'm doing. I recognize that for them to intersect, there must be a value of t and s so that the coordinates spit out here are equal to the coordinates spit out here. I can just, saying that another way, I need to find these particular values of t and s that make these 3 equations equal. So I'm going to look at the first 2 just to simplify things, and that gives me these 2 equations, which I can solve, right, a system of equations. I'll use substitution. This one's pretty easy to solve with substitution. From this first equation, I get t equals -1 minus s, which when I put in here, I get 3. I'm substituting -1 minus s in for t. The negative in front makes this +1 plus s equals 1 plus s, right? Well, now look what happens. We're getting nonsense. 4 plus s is equal to 1 plus s. In other words, s is the number, so that when you add 4 to it, it's the same as adding 1 to it, right? That's nonsense. If you want to take some more algebra, you can subtract s from both sides, and you can subtract 1 from both sides and get something like 3 equals 0, which is also nonsense. In any event, something's not working, okay? Well, whenever there's nonsense, either we made a mistake or there's a reason for it. So let's take a look at the graph of these 2 lines to see if we can discover what's going on here. So I've got them graphed here in GeoGebra, which is a pretty fantastic 3D graphing system. Here is the graph of these lines. I think the red is the x-axis. Yeah, that looks right. So we get a little view of what they're like. And it's clear from this picture, they're not intersecting. And it's interesting to see when we chose those 2, see if I can find the view. There it is. So I'm looking at this down now, looking into, it's like we're sitting above the z-axis or below the z-axis. I don't know, I'm not oriented, but we're sitting along the z-axis looking down it. So in essence, we're ignoring the z information, right? Just like we did, remember we did this by solving 2 equations and we chose the x and y equations. We ignored the z information and we said, find out where our x and y coordinates are the same. Well, if you look at these 2 lines, ignoring the z information, if they were, one way we could think about this is if we projected their shadows onto like a floor below, you know, it's not really possible because they're infinite, but that's the idea that the shadows they would make in the xy plane look like this, right? Lines that don't intersect. So we started our math by saying, let's find the intersection of 2 lines that don't intersect. The math spit back nonsense to us and said, these lines will only intersect if you can find me a number that when you add 4 to it, it's the same as adding 1 to it, right? That's That's the condition under which these lines intersect. And since we don't live in a world where adding 4 to something is the same as adding 1 to something, then they don't intersect in the world we live in. Okay, so what we have found is that these lines do not intersect, okay? Now, it does look like they're parallel when we look at them this way, but they're also not really in the same direction because, right, one's going very differently when we look at them, you know, in almost every other orientation. They have very different trajectories. So we wouldn't call them parallel. And these are what we would call skew lines, right? So this is the notion of skew lines, lines that don't intersect. All right, they don't intersect. It looks like I crossed it out. I was trying to underline it for emphasis. These are skew lines, they don't intersect, but they are not parallel, right? We determined they weren't parallel by looking at their direction vectors. If you do remember, when we looked at their direction vectors, the x and y components of v1 and v2 were scalar multiples of each other, right? The direction vectors for these two lines, we had v1 was 1, -1, 2, and v2 was -1, 1, 3, right? So if we ignore the z information, we get v1 is equal to -v2, right? This is not true in 3 dimensions, but in 2 dimensions, if we had these vectors in 2 dimensions, that's true, they are parallel. And so that's why that view we get looking down the z-axis shows them as parallel lines, because in the x, y dimensions, they are parallel. They don't ever share x, y coordinates. Okay, let's move on to another example. So let's go back here. Okay, one more example, similar kind of exercise. So let's look at 2 more lines. R1 equals t, 1 minus t, 3 minus 2t. R2 is equal to 1 plus 2t, 3 plus 3t, and t. Okay, so again, we can look quickly at their v vectors. We get 1, -1, -2. Oops, forgot my brackets. This one gives us 2, 3, 1. Right, so quick inspection, they are clearly not scalar multiples of each other, right? We'd have to multiply v1 times 2 to get this, but none of the other ones will work. And that means like there's no way to do it. Okay, so we'll try a similar trick. We're going to get the same kind of equations. Oh shoot, I should have done these in terms of s instead of t. It helps for the next step. So we're going to do the same thing, right? I'm going to equate t 1 plus 2s, right? I'm equating the coordinates just like we did last time. And I've got 1 minus t equals 3 plus 3s. These are the y coordinates. And let's just start by solving those 2 equations. Let me rewrite this a little better. Sorry, I'm skipping steps. So from R1, we get x1 equals t, y1 equals 1 minus t, z1 equals 3 minus 2t. From R2, we get x2 is going to be equal to 1 plus 2s, y2 is 3 plus 3s, z2 is s, okay? So same game, we want to set these equal to each other. We really want to do it for all 3, but we start with 2 of them. So I'll just choose the first 2 again. So I get I'm going to set these, I want x1 to be equal to x2, so I get t equal to 1 plus 2s, and my other equation is 1 minus t equals 3 plus 3s. Okay. So I've already got this one solved for t. It came that way, so I'm just going to shove that in there. I get 1 minus 1 plus 2s equals 3 plus 3s. So then what are we going to have? 1 minus 1 minus 2s equals 3 plus 3s. The ones cancel. I'll bring a 3 over here, so I'm going to have 3 equals 5s, or 3/5 equals s. I feel like I lost a negative. Oh, I did lose a negative when I subtracted the 3 over, so there's a negative in there. Sorry about that. So then it's simple enough to throw this value in here, and I'll get that t is equal to -1/5. Okay, so what did we learn? What we discovered with these two is that when s is equal to -3/5 and t is equal to -1/5, there is a point on these two lines that have the exact same x and y coordinates, right? So at this value of s and this value of t, this set of equations is solved, meaning they spit out the same things, okay? However, we need to see what it does in the z coordinate, all right? So let's just write this way. At t equals -1/5, R1 is equal to -1/5. I'm just plugging t is equal to -1/5 into this equation. 1 minus -1/5 gives me 6/5. 3 minus 2 times -1/5 is going to give me, so that'll be 3 plus 2/5. That's 15/5 plus 2/5 gives me 17/5. So at the only value where they have the same x and y coordinates, R1 has this z coordinate. Let's look at R2. At s equals -3/5, we get R2. Again, I'm just plugging in here. It works out to -1/5. 6/5, as we expected, they match in these coordinates. But the last term, the z term, we get -3/5. Okay? And so what that means is the only place where these two lines have the same x and y coordinates, right? Matching coordinate pairs, if we ignore the z, their z coordinates are different. And that was the only place they could possibly have intersected. And so because they don't have the same z coordinate, they don't intersect. So this is how you'll find intersecting lines. These lines, again, must be skew. They're not parallel, they don't intersect, they must be skew. If they were intersecting, the only difference is this number would have turned out to be the same as that one, and then we'd realize, oh, these lines have the same point. They contain the same point, okay? Let's take a look at this one on our grapher. Let's see. All right, so here's the lines now. These are our new lines, okay? So what we did, we found these 2 points. So we can clearly see they don't intersect, right? And if we look at them from a certain angle, it turns out we can find this place where they look parallel. That's from an angled perspective. Let's add in those 2 points that we found. So you can see, zoom in a little bit, there's a point down here and a point right here. Those are the 2 points. If you look at the coordinates on the left-hand side of the screen, those are the points we found where the x and y were the same, but the z coordinates different. Well, you can see the space between them on the z-axis going up and down. Let's look from straight down the z-axis. If we ignore that z information, they cross over each other, right? Right now, you know, if you weren't really thinking very hard about how the universe works, you might think my 2 arms are intersecting, but in fact, there's space between them. Well, that's what we're seeing on this image right here. They look like they're intersecting from here. The x and y coordinates are exactly the same at those points, but as soon as we look and change our perspective, we see that there's actually a pretty big gap between them, right? Between -3/5 and 17/5. So a gap of 20/5 or 4 units, right? We could fit a line of 4 units between these two. Okay, so that's it for this one. There's a lot to think about here. I know we're really smashing algebra and geometry together, which is awesome, but also takes some getting used to, and we will find varying degrees of success with that, right? Some people love to jump into this visualizing stuff. Some people, myself included, had to bang our heads against the wall for a long period of time before we could start really picturing these things. GeoGebra three-dimensional graphing is pretty great. So definitely I encourage you to check it out and play with it a bit. There's other ones online too. You might find some that you find more useful for yourself, but it is a great way to start visualizing things and understanding these pictures. Okay, that is it for this one. Thanks everybody. I will see you next time.